All right, so this is day 2 of the Kinetics of the Fading of Crystal Violet lab. I'm going to walk you through the lab, and then I'll show you the data analysis. And follow along. You should have hopefully watched the Kinetics lecture day 2 with the integrated rate law in it. So you should be able to understand what's happening in day 2. If you haven't, stop now, go watch that before you watch this, okay? All right, so like I said, crystal violet is a very bright purple colored compound, okay? And this is the structure of crystal violet. And you'll notice that it has this plus charge here. That's just a formal charge on the middle carbon, okay? And this version of crystal violet is purple, okay? This is the colorful version of crystal violet. It's purple. So this plus charge on this middle carbon, I'm just talking about the structure a little bit. This plus charge can actually move around. The formal charge actually, through resonance, moves to each of these 3 nitrogens, which is what you can see here. This nitrogen is now carrying that plus formal charge, and then sometimes it'll be this nitrogen, and sometimes it'll be this nitrogen. So through resonance, this cation is a very, very stable cation. Okay, we call this a carbocation. The carbon has sort of a plus charge. Okay, now I also want you to kind of see just, it's good to get used to seeing like organic structures so that you're not freaking out if you see something on the test. Is that this rendering of this molecule, the way that this structure is drawn, shows you the the 2 methyl groups that the nitrogen is attached to. But in this one, they just assume that you know that at the ends of these lines there's a carbon, and because carbon can't have a single bond, they assume that you know that they're also connected to 3 hydrogens each. Okay, so oftentimes carbons and hydrogens, the carbon is there, the end of the line means carbon, you can't just have nothing there, right? But they don't include the hydrogens because they think that you know that there are hydrogens, and you should know that there are hydrogens. Okay, so those are methyl groups that are not drawn there. Then let's look at what's actually happening in our day 2 reaction. So what we're doing is we're taking 25 micromolar crystal violet solution, and we're adding to it sodium hydroxide. The sodium is a spectator ion, so don't worry about it. So the hydroxide, we're adding 0.02 molar sodium hydroxide solution to this. And what happens is, this is the purple version of this molecule, right? You have the purple one with the Cv plus, the cation, the carbocation. And when you add the hydroxide actually donates a pair of electrons to this carbon and forms a covalent bond, and it changes the structure of the crystal violet, rendering it colorless. Okay, so it changes the way that light interacts with crystal violet, making it colorless. So we're using this reaction to figure out the kinetics, or do a kinetics experiment to figure out the rate of this reaction. Okay, again, I want to show you a different way of drawing. Here, the methyl groups are not drawn. They just tell you that the nitrogen is just connected to 2 methyl groups, like that, okay? And they expect you to know that it's like that. I just don't want you to get confused. Like, if you're looking at bonding or geometry, you should know that there are 2 methyl groups there, okay? Now, you're going from purple to colorless when 25 micromolar solution of crystal violet reacts with a 0.02 molar solution of sodium hydroxide. Now, compared to the 25 micromolar, the 0.02 is pretty high in concentration, okay? So here is what the reaction is. When you add, I want purple. When you add, so I want to have 10 milliliters. I'm going to do 10 ml of the 25 micromolar CV. And to that, we add 10 mLs of 0.02 molar sodium hydroxide. When they mix together, okay, when they mix together, this starts to become colorless. The resulting solution starts to become colorless. So remember, we are using a colorimeter for this part of the lab as well, okay? This is based on Beer's law. The Beer's law is used to figure out how much of a reactant is in or how much of a product is in our solution. So if the solution is going from deep purple to less and less and less purple, it's showing you how the concentration of the initial reactant is decreasing and being turned into the colorless product. You start out with a high concentration, you decrease, and the absorbance of the crystal violet is going to be less and less and less. Okay, the highest absorbance will be when most of the crystal violet has not reacted, and then as it starts to react, you'll see the color starts to fade and the absorbance becomes less and less and less, and the transmittance becomes more and more and more. Okay, so this reaction is actually kinetically rather slow. That's why we are able to do this experiment. Okay, it doesn't instantly fade. Like some reactions, you'll go from purple to colorless instantly. But this is pretty slow. We are doing a 900-second time limit, okay, to gather data for this lab. Okay, so let's talk about the rate laws involved in this reaction, okay? Um, when when you have additionally, or if you're writing the rate law for this equation initially, okay, here's your equation. You have CV, it's a big V here, CV plus OH minus is going to CVOH, okay? The reaction is right here actually, all right? That's your initial reaction. So if I were to write a rate law for this, okay, I would expect that it would be rate equals the rate constant. We're trying to figure out the order of the actual reaction, right? So it'll be rate equals rate constant, the concentration of CV, whatever order that is, which is to be experimentally obtained, and the concentration of hydroxide, whatever order that is. That is what you expect the rate law to be. However, there is a way to make this entire reactions rate law occur just because of CV, okay? And that makes it easier for us to do calculations, so, or just interpretation of data. So the concentration of hydroxide is so high compared to the concentration of crystal violet that the change in the concentration of hydroxide is going to be negligible. Only a few or particles or only a tiny amount of hydroxide will be used up. So the change will almost be negligible. So if you discount the concentration of hydroxide, you can still figure out the rate of this reaction or the order of this reaction just by looking at the CV. Okay? So you can actually write a new rate law. This is in your document, by the way. You can write a new rate law with a rate constant K prime, concentration of CV raised to the N. This K prime actually includes the hydroxide term and this K. We're just absorbing it into this K prime so that we just look at the concentration of CV and how that changes to determine the order of the reaction, okay? Because the hydroxide is so highly concentrated, changes in that concentration is going to be so negligible that really the rate will be really determined by the changes in the concentration of CV. So that's what we're saying, okay? So this is called a pseudo rate constant, and sometimes that happens in experimental situations, okay? Pseudo rate constant, and the pseudo rate constant actually includes the original rate constant, which is in pink, and the concentration of hydroxide raised to whatever order it is. But it's so negligible because the change is going to be so tiny. Okay, this term is not going to change much throughout the course of the reaction. All right, so this is the one that we're using for this day 2. Now, there is a video that I would like to show you. Oops, I've closed it. All right, I'll find it. All right, so this is a video of the lab technique involved here.
We will mix a solution of crystal violet. Right.
So this is 25 micromolar crystal violet, okay?
With a solution of sodium hydroxide.
So they're using 0.1, we're using 0.02, okay?
We will swirl the solution. We will then fill the cuvette with the solution. As a reaction.
Okay, so he's gonna use a different setup than us, but what he basically does is you take this cuvette, you put it into your colorimeter, and you close it after you've calibrated your colorimeter with your reference blank of distilled water. Once you close it, you cannot open it again, and you have to be as fast as possible in transferring the liquid into the cuvette and the cuvette into the colorimeter because the reaction has already started. The reaction starts the moment you mix the sodium hydroxide with the crystal violet, okay? It's already starting to slowly fade. Now, you put this colorimeter, you put this cuvette in the colorimeter, you close it, and you start to collect absorbance values on your screen, and you collect a point of data every 20 seconds until you reach 900 seconds, okay? The first few seconds of data you can't actually count because it's going to take you some time to get this cuvette into the colorimeter and to start collecting data. So the data that we have collected is sound from 40 seconds onwards, okay?
Basically spans sodium hydroxide and crystal violet react. The crystal violet undergoes a change and becomes colorless. We see the color fade with time.
So that was pretty fast because they used like a higher concentration of sodium hydroxide, but you saw that it went from purple to colorless.
The crystal violet undergoes a change and becomes colorless. We see the color fade with time. We will calibrate.
All right, so their setup is quite different from ours, so I'm not going to confuse you with that. So basically, you would have the same equipment, except our setup is slightly different than what they're using, or like more different than they're using. They're using different equipment, okay? But the method is the same. So here is the lab handout. I'll quickly show you. I've attached this to your page as well on Canvas. So you start to collect absorbance, and you would just write down the data until you get to 900 seconds. These first few seconds you can't really use because you have to actually get it into the colorimeter and collect the data. Now, once you've collected the data, what you're going to do is, based on the integrated rate law, you are trying to figure out what order this reaction is. So you have to make 3 graphs. The first graph is going to be just the concentration of CV in the y-axis and then time in the x. The second one will be natural log of the concentration of CV and then time. And then the third one will be 1 over the concentration of CV and then time. Whichever graph gives you a straight line will tell you the order of the reaction. Okay? Now let's relate this to Beer's law. Remember in the previous day 1 video, you have gotten the molar absorptivity constant, right? From your Beer's law data, you have your molar absorptivity constant. We got it. It's 0.0622, right? So that 0.0622 is going to be super valuable because right now, so here is the data, okay? Um, let me explain why the molar absorptivity is important, and then we'll look at the data. So you have Beer's law, which is A equals molar absorptivity constant times path length times concentration. Now you have absorbance values that you just collected. So look at this data. These are absorbance values from 5 groups, different colors, for 900 seconds. So you have your absorbance values. You know the path length is always 1 centimeter. You have your molar absorptivity constant, which is 0.0622, okay? Molarity centimeters. So now you can actually calculate your concentration because this is your unknown. In order to plot your data with concentration, natural log of concentration, and 1 over the concentration, you actually need the concentration based on absorbance, which is why it's important to make a calibration graph to calculate concentration. So concentration is just going to be absorbance over the molar absorptivity constant times the path length. Since the path length is always 1 centimeter, it'll just be molar absorptivity absorbance over molar absorptivity. So here are my 5 groups of data. I've taken the average absorbance right here. So I have a whole column of average absorbance values. So in order to obtain the concentration of CV, I just have to divide the absorbance by 0.0622, and we are ready to start graphing. Okay, so let me just double check it. It's 0.0622. Okay, so let's make some graphs. I've already set up the graphs so that they'll populate as I populate the data here. Okay, what is this? All right, so here's absorbance. You can do this on your Google Sheets too. You select the cell, you type equal, then you select your absorbance value, and then just type divide by 0.0622 and type enter. Once you have your first value, you can grab the corner of this cell and just drag down to get all of your concentration values. So look at that. You got all your concentration values. The concentration of CV at each absorbance. When the absorbance is 0.799, here's the concentration of the CV. Okay? And here's your zero order graph with, it's kind of curvy. Okay? Here's your concentration on the y-axis, time on the x-axis. You want the straight line, not the curvy line, okay? So it's not zero order. So let's do ln of the concentration now. So this is equal, type in ln, parentheses, click your cell, close parentheses, press enter, hold and drag down. You got your ln of CV. And let's do this one too. Equal 1 division sign. Whoops, wrong cell. Press the concentration of CV, so 1 over the concentration of CV. And then drag down. There we go. So now you have all 3 sets of data. Super easy to analyze with Excel or Google Sheets, okay? So kids, look at these 3 lines. Got your zero order. This is curvy. You got your second order. It's going to have a positive slope, but still a curve. The one that has the nicest fitting line, we have slight issues there. Just experimental data, right? Never going to be perfect. But look at that nice line. So this order of the reaction is first order. We know that based on first order reactions. I'm going to put a trend line in here. Okay. I wonder if I can. There we go. I have a trend line. That's the straightest line here. And I'm going to do display equation on chart, set the intercept. Whoops, why is he going? Oh, I don't want the intercept to be 0, 0. And there's my R square value. You can actually set the intercept to be 25 micromolar or 1 over 25 micromolar. I mean, sorry, not 1 over, natural log of 25 micromole. Okay, so here is the equation. Now let's zoom in. So we've determined that it's not zero order, it's not second order because zero and second order are curvy. First order is a straight line, okay? And the slope is your rate constant. There's your rate constant, 0.0011. Very small, which is why this reaction is so slow. And the R-square value indicates that all of the dots are very close to the trend line. So this is good data, precise data, okay? And that is where your y-intercept would be the line 2.6109. That is the natural log of the initial concentration of CV that you started with. If you wanted to just find the concentration of CV from the natural log, you can do that too, okay? Using log rules in the E term. Okay, so there it is, day 2 of the crystal violet fading lab. So it's very important what you understand here. You're going to have to apply it in FRQs later on, okay? All right, peeps, have fun doing the FRQs.